Now we're getting into really trying to understand the force involved in electrical behavior. Electric current is simply the rate at which electric charge flows. Electric current is given the designation I and is found by taking the amount of charge moved past a certain point divided by the time it takes to move them. This gives us units of 1 coulomb per second, or 1 ampere. So what we are looking at is the cross-sectional area of a particular wire. The number of charges that are counted going past that area in a given amount of time is what we refer to as current. So let's start off easy. What is the current when a battery sets 720 coulombs of charge in motion in 4 seconds? Well, current is charge over time, so we plug in what we know in our equation for current. We get a value of 180 amperes. Now 180 amperes is a pretty large current, so it indicates that there's a lot of charges moving through in a short amount of time. If you think about the amount of force it would take to start an engine of a truck in motion, it makes sense that you would need a lot of charge to do that. Then how long does it take for 1 coulomb of charge to flow through a calculator if 0.2 milliamps of current is flowing? In this case, we are trying to find the time involved, so we need to rearrange for time, and then plug in our knowns to find 3.3 times 10 to the third seconds. 3,300 seconds is just shy of an hour, so our calculator takes a longer time to move a much smaller amount of charge than our truck did. If you think about it, the calculator does not have all of those huge moving parts, and so requires very little energy to operate. So why are all these charges flowing in the first place? Well, first we need to set up a circuit. This one pictured is about as simple as you can get. We have a battery. A battery produces electricity by transforming chemical energy into electrical energy. There are a lot of different types of batteries, but the simplest contain 2 plates or rods made up of 2 different types of metal, although one of them could be carbon. These electrodes are surrounded by paste or solution called the electrolyte. This whole thing is called an electric cell, and you can have several cells connected together to form the battery. The section of each electrode that is not submerged in the electrolyte is called the terminal, and that is where wires can be connected. In this example, we have sulfuric acid as our electrolyte. The acid will dissolve the zinc electrode and release zinc ions into the solution. The zinc atoms each leave behind 2 electrons on the electrode, causing it to become negatively charged while making the electrolyte positively charged. This new positive solution can then pull electrons off the carbon electrode, leaving it positively charged. Now that we have 2 opposite charges on our electrodes, we have a potential difference between the 2 terminals. If charge is allowed to flow between the terminals, then more zinc can be dissolved. It is convenient to represent our circuits with a schematic drawing. Certain symbols are used to represent the different parts of the circuit. The battery is represented in the schematic by the 2 red lines. The longer line represents the positive terminal, and the shorter line represents the negative terminal. And yes, this is important, and it must be represented this way. The battery is connected to some type of load, in this case a light. Now, a squiggly line that represents a light in this case is actually the symbol for a resistor, but it can be used to represent any type of object that slows down the flow of charge. We know that like charges repel each other, so the electrons with their negative charge are moving out from the negative terminal of the battery and flowing into the positive terminal of the battery. We know that this schematic represents wires connected to a light bulb and battery. We also know that in metal wires, the current is carried by the electrons as they move through the wire. But notice the direction of the current in the schematic. It shows the current moving from the positive terminal to the negative terminal. Benjamin Franklin did a lot of experiments with electricity, and in the 1700s he was fairly limited in the experiments he could do. So he really had no way to know if it was the positive or the negative charges that were moving, so he simply defined current as the moving in the direction that the positive charges would flow. Now there are situations where there are moving positive charges, such as ionic solutions or nerve cells, but those are special situations that you might run into more of a chemistry or biology realm. So inside a wire, the current is actually moving in the opposite direction of where the negative charges are moving. It is important to note that there is an electric field being produced that is responsible for the movement of the charges. If the electric field is from left to right, then the electrons will feel a force pulling them to the left. As these electrons move to the left, that area builds up a negative charge. Then over on the right, there is a buildup of positive charges. So the negative charges moving left is essentially the same thing as protons moving to the right. And really it is much simpler to think of the positive charges as moving in the direction of the current. They don't, but it makes things easier to talk about. So since we define the direction of current as the direction of positive flow, then the current is said to be moving to the right, or in the same direction as the electric field, but opposite the direction of the velocity of the electrons. Now we say that the electrons are flowing with some velocity. Reality, of course, is not quite so simple. The electrons experience all kinds of collisions with atoms and other electrons as they are being pulled towards the positive side of the electric field. So the path is much more random than you might envision when we talk about flowing electrons. When we refer to the velocity of flow of charges, we are actually referring to the average velocity, or what we call the drift velocity. We can also describe the current in terms of the number of charges per unit of volume. Our wire has some cross-sectional area A, and if those charges travel for 1 second, they will travel some distance x along the wire. There are a certain number of electrons, n, within that volume, and each electron carries a charge of q. We can use these as another way to describe the current flowing through the wire. The current is equal to the number of electrons times the charge of each times the cross-sectional area times the distance the electrons travel divided by the time.